Oh, hi. I brought in some samples of some what we call transition metal complexes. And these transition metal complexes all have transition metals in them. And the transition metals are the 10 groups in the middle here, including things like chromium and manganese and copper and zinc. These transition metal complexes are formed because we have transition metals surrounded by what we call ligands. There's things on the outside of these transition metals. These transition metals have a charge on them, for example, copper 2+. And I have a copper 2+ transition metal complex right here with that beautiful copper blue. And these structures are all octahedral. They're all octahedral. And I made up some models to show you. Octahedral complexes, what we have is our transition metal ion in the center, surrounded by 6 of these so-called ligands at 90-degree bond angles. Nice and symmetrical. Looks beautiful. I have some color coding here because we'll consider a couple of different complexes. Okay. So one that I'd like to consider with you is going to be this copper 2+. So let me write a formula for this copper 2+ transition metal complex up on the board. There is in fact some copper 2+ in here. This one happens to be surrounded by 6 chlorides. So we have a copper 2+ in the center and 6 chlorides. Now if copper 2+ right there is 2+, and each chloride is -1, what would be the charge on this entire transition metal complex? This portion right here. If this is +2, and each chloride is -1, then the whole piece would have a charge of 4-. Now that's not what's inside the bottle. We can't have just this piece. This looks like a polyatomic anion. Many atoms with a charge that's negative on there. We have to have offsetting charges. So in fact, we have a 4+ charge in the sense that we have 4 potassium plus ions. So the whole thing is neutral. Having said that, it's like a salt. Sodium chloride, sodium +1, Cl-, but it's just a little bit busier. We have 4 positive charges and 4- on this whole piece. Now in space, we're going to go ahead and put the copper 2+ in the center, and then put 6 bonds around it, top, bottom, left, right, front, and back. So let me put a couple of bonds, top, bottom, a couple of bonds, left, right, a couple of bonds, front, and back. Now those top and bottom portions are usually called north and south pole to give us the impression that this is the Earth and things work out nice there. Let me go ahead and put a Cl- and a Cl- and some Cl- around the equator. So these are equatorial positions. And we get the feeling of the Earth again. Now this whole piece has a 4- charge. I can put big brackets around this, 4-, and indicate that there are 4 potassium plus ions floating around or in the crystal structure. And that's a beautiful picture. This is octahedral. We like to abbreviate octahedral as O and then subscripted lowercase h. Octahedral, meaning 8 faces. There are 8 faces to this structure. Let me draw one of them now. It's a triangular face. Try and think about where the other 3 are going up, and then there's 4 more going down for a total of 8. We have these triangle faces making pyramids. So 4 of these triangles make a pyramid going up, and then 4 would be pointing down. So we have 8 faces. Bond angles 90 degrees. And this particular complex, because we have 6 chlorides, 6 of all the same, renders this nonpolar. Beautiful and symmetrical. Now let's go ahead and make another transition metal complex and make it a little bit more complicated. And instead of having 6 chlorides, let's mix things up and maybe have 2 chlorides, 4 fluorides. So I propose a new structure. CuCl2F4. Two chlorides, 4 fluorides. Fluoride has the same charge as chloride, a -1. Now let's go ahead and draw this out. Copper 2+ in the center. North and south poles for equatorial positions. And we have choices to make, but in this particular case, I'm going to put a chloride on the top and a chloride on the bottom. This is the choice that I make. This will differ in the next example. We can as you might imagine, have the chlorides next to each other at 90 degrees instead of across from each other. Now that leaves the 4 positions across the equator for the fluorides. Bond angles are 90 degrees, octahedral, and take a look and see if you can determine if this thing is polar or nonpolar. This is octahedral, bond angles are 90 degrees, and does that look polar or nonpolar? In fact, it's nonpolar. The chlorides are opposite, as of each pair of fluorides are opposite as well, so there's no net dipole. Now, we could put this together differently. Instead of me putting square brackets and -4 and potassiums, I'm not going to do that. We'll just leave this as it is and draw its counterpart over here. North-south positions, 4 equatorial positions, but in this case, let's put the chlorides next to each other. A chloride here and say a chloride here. Now you didn't have to put your 2 chlorides in these positions. If you want them next to each other, you could have selected here and here, here and here, and these 2 positions. It doesn't matter because all we have to do is just rotate it in space and have the same structure. But here on the right, that's different than the one on the left because we don't have chlorides across from each other. They're next to each other. The fluorides fill in the other positions. Octahedral complex, bond angles based on 90 degrees. And take a look and determine if this is polar or nonpolar. I wrote down octahedral, 90 degrees. Is this polar or nonpolar? It's polar. It's, if you will, not symmetrical. Chlorides on one side, fluorides on the other. So this one turns out to be polar. Both of these have the same formula, this formula that's written up here on the left. Both of them have very similar properties, but some different properties. These are going to have different densities. Since this one's nonpolar and the one on the right is polar, they have different magnetic properties. They behave differently in magnetic fields. They will have different melting points, different boiling points. These are geometric isomers. Geometric isomers. Isomer, iso meaning the same and mer meaning unit, so these have the same unit or the same formula, but they're put together differently in space, the geometric isomers. The one on the left we go ahead and call the trans isomer. Let me put a sweeping arrow here and label this trans. The reason we call it trans is like across from, like the Transcontinental Railroad across the United States from East Coast to West Coast. Chlorides are trans, or across from each other. You could say the same thing for the fluorides. They're also all across from each other. Over here, the chlorides are next to. Let me put a little arrow here and write cis, meaning next to. So trans is across and cis is next to or adjacent. And we don't have really the case here for fluorides. You could say, well, some of the fluorides are across, these 2. And we're focusing on this idea that we have 2 chlorides. So we have cis and trans isomers. Let me show you these on models. So, the cis isomer and the trans isomer. The trans has the chlorides in white across from, and the cis has the chlorides next to. This is nonpolar, and this one's polar. We have this stuff on your right, not the same as your stuff on the left. We just finished the cis and trans isomers because we have 2-4 combo, 2 chlorides, 4 fluorides. But what if we have a 3-3 combo, such as, oh, and let me choose a different transition metal this time. I'm going to have zinc 2+ when this is said and done. And let me go ahead and choose Br3I3. Rather than putting a K4 out in front of here to offset the charge, let me just focus on this anion. Zinc 2+, bromides, iodides, 4- charge. Let's go ahead and put our zinc 2+ in the center and set this up for north and south pole and 4 equatorial positions. And let's do another one over here on the right. Get this thing started. North-south pole, 4 equatorial positions. Now, 3 bromides, 3 iodides. Let me go ahead and choose I'll choose iodide. Let me go ahead and put 3 iodides in here. I'm going to choose to put the iodides north and south pole, and that's going to leave me with no choice. One has to go at an equatorial position. It doesn't matter which one I choose. Any of these 4 will give me the same structure. I'll have north and south pole, one over here. If I don't like that and say, well, I want it over here, all I have to do is just kind of walk around the molecule or turn the molecule and say, it's the same. Let me go ahead and put it over here. I'm going to forego the brackets and the charge on this. On this side, I am not going to put the iodides across from one another. Let me group them so that none of the iodides have a partner at 180 degrees, so they look like they're in one corner. The empty spots are occupied by the bromides, and I'm not going to put those in. I don't want to distract from the iodides here right now. Over on the left, the iodides are making what we call a meridian. If you could, and you can't, travel from the North Pole along the globe down to the South Pole, you would be walking a meridian. Some people look at it and call it half of a circle, and that's just fine. So for short for meridian, we have the Mur isomer. And I'm not making this up, that's its real name, a Mur isomer. So that's the meridian or Mur isomer with 3 of these leading to 180 degrees around. We don't have that case over here. We're not going to be able to go 180 degrees around. That's not what that represents. In fact, these 3 iodides are all in one face, making up a face. And we like shortcuts, and this is a real time saver. Instead of calling this the face isomer, we leave off the E and call it the FAC isomer. And that's not a fake name. We have Mur and FAC isomers, as silly as that sounds. Let me ask you something. Polarity. I'll give you a hint. Both of these are the same. So either both of these are nonpolar or both of them are polar. And have a look for a moment. Both of them are in fact polar. They're lopsided. The iodides cancel, but then you're going to have one iodide off to the side. Let me put the bromides in. And the bromides on the meridian structure in themselves will make up a meridian. So let me go ahead and show a sweeping arrow for the bromides, and that's making up a meridian as well. Over here, the bromides make up a face, just like the iodides did. And I think I will go ahead and sketch in that little triangular face here and show you. Bromides on one face, iodides on the other, polar. So both of these are polar, both of these are octahedral, both of these have bond angles based on 90 degrees, and both of these are polar. So we have 4 isomers, cis and trans, Mur and FAC. A quick review. Mur and FAC take place when we have 3-3 combo. Cis and trans take place when we have 2 of one thing and 4 of another. Those are the only isomers we have with these octahedral complexes. If you have 6 of one thing, for example, ZnBr6, there's no isomer. If you have ZnBr5I, you don't have isomers. It's polar, but you don't have any need for an isomer. You can't create multiple representations of that. Let me show you the Mur and the FAC isomers using these little models. If I select the reds to be the iodides in our previous example, they make a meridian, and the bromides make up a meridian also. So travel from north to south pole. You could say, well, I can travel north to south pole and just rotate this around a couple of times. The FAC, or the face isomer, I took the world's greatest invention, duct tape, and made a little triangular face there showing you the face from the red ones. I could do the same over here